table of results for the pink Aurora algebra. Now, thus the pink Aurora algebra forms a group structure. My face from that television or presentation is exactly what we are going to unfold later on. So, we need to ensure that all these conditions are satisfied under pink Aurora algebra to prove that it is indeed a group or it forms a group structure. So first one, is it close? The second one, is it associative? Third one, is there an identity element? And the last one is, does the elements has inverses for all? Now here we are going to prove the closure property. So is it closed? The set of elements are MILESGAR 1, 2, 3, 4, 5, 6, 7, 8. The set demonstrates closure because when any two elements are combined, the resulting elements always remain within the original set. This ensures that all operations produce familiar outcomes without introducing any new external element. Therefore, the closure property is satisfied. So is it close? Yes, it is close. Now, the associativity property. So is it associative? To check if the table of results of the pink Aurora algebra follows the property of associativity, we need to turn the table upside down by rotating it to 180 degrees. After flipping, the table should still show the same arrangement as before. If the positions and result remain the same after the flip, it means that the model is associative and the order of combining all elements does not affect the result. So let's check our table after rotating it 180 degrees. So this is the table, the original table. Now after we rotate it to 180 degrees, this would be the result. So this is the result now. And we are done rotating the table to 180 degrees, we need to perform different moves so that it would still match our original model and to show that it is associative. So here are the moves that we need to perform. We have a complete set of 12 moves. So take note that after every move stated above, we need to delete the repeated row so that it would not be confusing. And that is also the reason why rule 8 and rule 15 are repeatedly mentioned. It is because they replace the deleted rows. So take note of that. So now, this is our table after rotating it 180 degrees. So let's start with the move. So the first move is to insert row 7 between row 1 and 2. On this is the result of inserting row 7 between row 2. Second move is to insert row 8 between row 2 and 3. And this is the result of inserting row 8 between row 2 and 3. Now, we need to insert row 8 between row 3 and 4. And this is the result of inserting row 8 between row 3 and 4. Next is to insert row 8 between row 4 and 5. This is the result of inserting row 8 between row 4 and 5. Next is to insert row 8 between row 5 and 6. This is the result of inserting row 8 between row 5 and 6. Next is to insert row 8 between row 6 and 7. This is the result of inserting row 8 between row 6 and 7. Next is to insert row 15 between row 8 and 9. This is the result of inserting row 8 between row 15 and row 8 and 9. Next is to insert row 15 between row 9 and 10. This is the result of inserting row 15 between row 9 and 10. Next is to insert row 15 between row 10 and 11. This is the result of inserting row 15 between row 10 and 11. Next is to insert row 15 between row 11 and 12. And this is the result of inserting row 15 between row 11 and 12. After that is to insert row 15 between row 12 and 13. This is the result of inserting row 15 between row 12 and 13. And last but not the least, we insert row 15 between row 13 and 14. And this is the result of inserting row 15 between row 13 and 14. And below is the result after performing the moves to prove that it is associative. So Can you see that it reflected the original table of our pink aurora algebra? So now, is it associative? Now that we have performed the moves that we need to show that our table is associative, we can see that it reflects our original model, and therefore we can say that our geometric model is associative. So based on our checklist, we have checked two so far. Now, we are going to the identity element. So, is there an identity element? So, since there is an intersection between the row and column in the table where the arrangement of elements remains the same as the order found along the outlines of the table, it confirms the existence of an identity element. In this case, the identity element is M, as it leaves other elements unchanged when combined with them. So, as you can see from the pictures, the bold M letters, they are the identity element in each element. So, is there an identity element? Yes, there is an identity element. Now, next one is, does the elements has inverses? We are going to prove this with respect to the inverse element. So, does an inverse element exist for all? So, to determine the inverse of each element, it is necessary to identify first the identity element, which is M. So after identifying the element, we can now find the inverses of each element. So this means that the inverses of each element are as follows. So N inverse is M, I inverse is R, L inverse is A, E inverse is G, S inverse is S, G inverse is E, A inverse is L, R inverse is I. So the back elements, which would be 1 inverse is 1, 2 inverse is 2, 3 inverse is 3, 4 inverse is 4, 5 inverse is 5, 6 inverse is 6, 7 inverse is 7, 8 inverse is 8. So, does an inverse element exist for all? So, yes, an inverse element exists for all. So, the geometric model satisfies all the four required properties of the group. So, as I said on my introduction, the math club member or the magic math club that we have has four rules, and it is reflected in our geometric model, which is the pink aurora algebra. So to summarize everything that we have talked about from this video, we have first the closure. So the closure element states that the set demonstrates closure because when any two elements are combined, the resulting elements always remain within the original set of 16 elements. No operations create new elements outside of this element. So this confirms the closure property is satisfied. So closure property is checked. Next one is the associativity. So the elements represent geometric transformations such as rotations and reflections. Since composition of such transformations is always associative, shown by rotating and interchanging the table using manipulation, the associative property is satisfied. Next is the identity. So the element M serves as the identity element of the group because when M is combined with any element, it leaves the element unchanged. Similarly, combining any elements with M also leaves the element unchanged. This confirms the existence of an identity element in the group, which is the M. So identity is checked. Lastly is the inverses. Every element in the set has a corresponding inverse element. So yes, we have proven that a while ago, so it is checked. Now, our geometric model pink aurora algebra satisfies the four properties needed for a group. So it means that our pink aurora algebra indeed forms a group structure. So that is all for this video. I just want to give you my deepest thank you for cooperating and listening, and thank you for your attention. So again, this is Millicent, and thank you for watching my video. Goodbye.